We're still doing rate of change in social sciences now, so the good news is we're staying just on 3.3, so even though it looks like we're not going to have a 3.3 video on there, but it's pretty much the same thing as 3.4. We're just looking at rate of change in a different perspective and a different, like looking more at money and different things like that. So although calculus has been applied to the natural sciences for centuries, it's only been It has only been recently that social sciences such as psychology, sociology, urban geography, and economics have been making use of calculus. Psychologists interested in the theory studied the so-called learning curve, which graphs the performance level of someone's learning skill. So a lot of learning skills have been tested using calculus. I can't say words today. Sociologists, I can't say that today. Sociologists, thank you. There we go. Use calculus to analyze the spread of rumors. So like how things, fads, fashions, stuff like that, they use for rate of change of that, especially with social media today, how things spike in terms of people talking about it, tweeting about it, all those things. And then economics, obviously, maxing out revenue, cost of a function, kind of its peak time to sell, those type of things. Okay, so all three of those we're going to kind of look at. Yeah, marginal cost as well. So the limit of this quantity as change of x to 0, the instantaneous rate of change of cost with respect to the number, number of items produced is called the marginal cost by economists. Just really striking out today. Sorry. I know. So that's actually what it is. It's like, oh yeah, that's right. Okay. Marginal cost. So the marginal cost in this case would be the change in cost over the change of what the item is. So x just refers to the item that we're talking about. Okay. So dc over dx. Okay. Since x can usually take on only integer values, it doesn't really make literal sense for x to approach 0, but we can always make it replace it in terms of by the whole function, the cost function, as a smooth approximation. So what it's saying there is that we're not going to really approach anything in the negative sense for cost in terms of we'd be owing. So we want to stay a little bit more towards approaching the maximum or the minimum of what we're looking for. Are we trying to minimize cost or maximize profit? So like right now, if we have marginal cost, we're trying to make that as small as possible because we want to make sure we're above that. Okay? And so then we would still, in this case, still use the derivative of it. They set up the definition of the limit here in terms of n plus h minus c of n all over h, but we know that as c prime. Okay. All right, so therefore, the marginal cost of producing n units is approximately equal to the cost of producing one more unit. So that'd be your units is n and n plus 1. So we look at that relationship. It's often appropriate to represent the cost function by a polynomial. So the cost function here, a plus bx plus cx squared plus dx cubed, etc. Where a represents the fixed cost. So that would be your starting amount, your amount to run the factory. If you're making something, that's your fixed cost. It won't change. Like they said, rent, heat, maintenance, etc.
What's the equal sign with the dot above it? Like it was on the last page.
Last page. Equal sign with a.
At the bottom.
Prime. Oh, it's just the change from one to the other. I don't know what that signifies, but it's just showing you the derivative of the change of the original n plus the next item. So it's a change what we do is we have to look at if we make 20 shirts, we're going to look at between 20 shirts and 19 shirts and look at that change. So that's what this is talking about. I don't really know what the dot signifies though, sorry. I'll figure that out for you.
Yeah.
But it's good eye there, Jose, good eye. Okay, so let's actually look at something that's a little bit more applied here. So Quinton Mills is a large producer of flour. Management estimates that the cost in dollars of producing 5 kilogram bags of flour is this cost. So that's your cost function. Okay, find the marginal cost at production level of 1,000 bags. So in our mind, what are we going to do? Right, marginal cost means the rate of change. So we're going to go with the rate of change, and that means to us we're doing C prime. So C prime, that's gone. That's just a constant now. We're going to have 0.0002x. That's our new function. And now we're going to put 1,000 in for x. This is for part A. So I put 1,000 in. It's going to give me roughly 43 cents per bag. And so, actually back to what Joe said about that equal sign with the dot, now we're going to find the actual cost of producing the 101st bag, and that idea is we're going to do 101 minus 1,000. Because if we do 101 minus 1,000, you can figure out how much it costs to make that one bag. So you're going to do, that's what this was right here. I'll come back here. That's what this was. The one after and the one before. So we're going to do the one after. So we're doing C, just regular C, of 101. So we're going to calculate that from the original function. And when you do that, you end up getting the same thing, which is just proving the derivative works. Okay, if you want me to, we can't. I'll write it here. So if So that's what you would calculate. That's the first one, and you plug in the second one. So you can see, sorry, this is the second one. Yeah. Plus. Oh, this is just the first half. So that right there is the first half, and then I would minus this plugged in for 1,000. See what I'm saying, Dana? I'm just not going to write that one. I was just showing you what I didn't write to get there. Okay, just a calculation. Okay, I do like this section though. I think the money stuff's a little bit more interesting to me, at least. But of course, the businessman's interested not only in the cost, but also the revenue and profit. Let P of X be the price per unit that a company can charge if it sells X units. Then P is called the demand function, so that's how much the demand is. So this would be right there. If X units are sold and the price per unit, then the total revenue is X times P of X. So X units times the demand of units. R is called the revenue function. R prime of the function is called the marginal revenue function. So the derivative of your revenue function is called the marginal revenue function, which is the same thing as marginal cost. Your cost function, the derivative of that was marginal cost. Derivative of revenue is your marginal revenue. What do you see might happen here? What type of rule do you think could come into play when you're doing marginal revenue? Yeah, potentially the product rule, right? Because you have X times P of X. You have a product of two things. Okay, maybe not. Might multiply in and be okay, but just something to think about. Okay, I'll pause it for a second. All right, so get to this first example here. Or example 2, sorry. Howard's Hamburger has taken a market survey and has found that the yearly demand for their hamburgers is given by that. So that's the demand function, 800,000 minus X all over 200,000. So graph the demand function. So we want to graph the demand function roughly. you'll see that like if you plug in 0, what do you get? What's 800,000 divided by 200,000? So you're seeing you're going to have fairly small numbers for your y. So that's like your first value. 0 is 4. And then it just kind of keeps going that way all the way to 800,000. Why I say 800,000? Because if I put 800,000, I get 0, right? So that means my demand will be 0, 800,000. So it's pretty much essentially it's a small slanted line that's going to go that way if you plot it. Obviously, you can be a little bit more exact if you'd like, but that's the track it's going to take. So for example, if I put in 200,000, so 200,000 would be like here. That would be 600,000. 600,000 divided by 200,000 is at 3, so then it would be a dot at 3, etc. Very, very linear equation. It's very simple. For B, what's the demand for the hamburgers corresponding to the prices? So at 0, so what's the table here? So we have, let's actually do this rectangle. This might help a little bit, be a little bit better. So I'm making this table. So this is A, the rough graph. Here's a table. So it wants to know P. Okay, so it wants to know what's the demand for hamburgers corresponding to the prices. So how many people want the hamburgers when they're free? Well, that'd be 800,000, right? Like that's, if they're free, everybody wants them. That makes sense. Okay, the demand when they are 50 cents. So demand when they're 50 cents, that's 700,000 people want them. When you're doing $1, it's 600,000. $1.50. It's 500,000. You can just see it's that linear relationship still. That's a 50. $2. 400,000, and then etc. Okay, I'll let you finish that off, but if you go all the way to 4, 4 would be 0. So really quickly though, so first off, the one thing we have to understand that P, what does P stand for? Let's go back to here real quick. So P isn't the demand, is it? What is P? The price. So make sure that you understand, that I kind of glossed over it a little bit, but make sure you understand that when we're doing this, we've been doing XP, right? That's why if you're not like, how'd you get 4? Well, if I put in, for example, if I do X is whatever, $2, okay, we subtract it, we're going to times it by 2 as well. Sorry. If we put in the amount of people, 600,000, okay, whatever that output, that's going to give us the X that we're going to plug in as well. So let me just say example. Let me do 600,000. If I do 800,000 minus 600,000 all over 200,000. 800,000 minus 600,000 is 200,000, which gives me 1. So that's 1, right? But then we have 600,000 here for the X. So 600,000 times 1 gives me that output in the demand function. Okay, just make sure, please don't, it's not just P of X. I don't want you to think it's just P of X. It's X of P for the demand function. Okay, so why that's important is because now we're going to find the marginal revenue when X is 300,000, which means we need the derivative. Okay, so we're not taking the derivative of that, we're taking the derivative of we're going to multiply that X in. Okay, x just goes to the top, right? So when I do the derivative, so all I did was I just times the x here. So I can take the derivative of it. If I take the derivative of it, the demand prime my brain isn't working today. So that's the derivative, because all I did was the x comes off, 2x. That's my demand function's rate of change, like that's the derivative. So now we would plug in 300,000 there. Yeah. Because there's no x there. Okay. So that's the same thing as like, because if I pulled it out, it would be 1 over 200,000, which would be a constant in front of an x, and so it wouldn't, it's irrelevant. Okay. So when we plug that in there, to plug in the 300,000, that gives me 600,000, that gives me 1 again. So that means $1 per hamburger is the rate of change at that point. So at that point, they're changing by $1 a hamburger. So all I gotta do right there is just plug in the 600,000 to right here, or excuse me, the 300,000 to right here. And it'll give you $1 per hamburger. Okay, all right, so let me recap this one more time, because I think we'll see a little bit of confused faces. So XP represents the demand function. This is just the price function. So when I graph the demand function, I have to graph XP. So that means pretty much I need to graph this. Now these are just, we just plug those in. So for example, I just plug in 200,000 into there. And then I'm going to divide. Okay, once I do that, it's going to give me, you know, if I put 200,000 in, it should give me, what do we say for that? 200,000 was like $3. It's going to give me whatever value when you plug that in. That'll give me the points that makes it linear. Then we have the table here is the same exact thing. It's just actually putting these points into a table. So A and B is just kind of labeling the demand function in terms of points. And the last part, we took the derivative of the demand function, which we did there at the bottom, and we figured out what the rate of change was for 300,000 people, which means $1. Okay. All right. Okay, so then saying the same type of question. Estimates the cost in dollars of making X hamburgers is 125,000 plus 0.42X. Use the demand function example of 2 to find the profit and the marginal profit when X is 300,000 and X is 400,000. Well, what is profit? Revenue? Close, but just think about it just in general. How do you define profit? Which is revenue minus cost, right? That's what profit is. Everybody understands that basic principle? Everything you take in minus what it cost you, that's your profit. Okay, so then we know that, for example, our revenue is the one we just had, the demand. Okay, so it's going to be the, I wrote it like this just for the sake. That's the revenue. Our cost they gave us. Okay, so then what we want to think about is, it says for A, we want to figure out the marginal profit when X is 300,000. So what do you think marginal profit is going to mean? Okay, derivative, yeah. But so do you see this right here? Like this we just wrote out, that's our P of X, right? So if we want marginal profit, then we're going to want P prime of X. Okay. All right, so we already know what this one kind of shapes out to. It's going to be, and then we have that one's 0.42. So we're going to go, I'm going to go and divide this. So 4. That's why I have this, okay. Okay, let me explain that. So I took the derivative. Okay, so 800,000 divided by 200,000 is 4. So this is technically 4x. And then derivative of 4x is 4. Here, derivative of x squared is 2x. So it'd be 2x over 200,000, which is 1 over, like if I do 2 over 200, is 1 over 100. So I just simplified the fraction is all. Okay, and then why this is helpful is because then what we're going to do is that derivative is gone. We're going to minus the 0.42. That's all we have to minus. Because the derivative of 0.42x is just 0.42. And that's where I got this. So our profit function. Combine your like terms. 5/8, yep. There's your marginal profit function. Now we can just plug in our values for A and for B. Just hang in there. This is the last example. I know we're dying. And so when I plug in 300,000, you're essentially going to get 3. 358 minus 3 is 58 cents. That represents how many profit per hamburger? 58 cents per hamburger. That's our marginal profit. For B, 400,000. We're losing, because it's going to be 4. 400,000 divided by 100,000, that's 4. 3.58 minus 4, we get negative 0.42. So that means we're losing money there. Okay. So basically you can see that we must be selling them at a pretty cheap price where it's going to cost us money at some point. So if we're going to have actually more people buy, we're going to want to charge more for them so that we don't lose money. So basically, yeah, that's the best way of looking at it. Okay. All right, so that was all.